Hello, and welcome back to Stat 3050 at the University of Wyoming. We are online, but I'll tell you what, we're having a good time. We're hanging in there. So today I have a quick example on how to do simple linear regression in R. And so from here on out, in these examples, I sort of have these goals here. This case we have a lot because this is our first time looking at an example in R. That's fine. So these 7 here, we're going to meet every single one. It's going to be awesome. It's going to be tight. So the first one, introducing simple linear regression in R, and then plotting the relationship between two variables. We have a really cool data set that we're working with. A little bit more on that in just a second. But we're going to be using a scatter plot, and more specifically, we're going to be using the ggplot2 library from the tidyverse. And then we're going to build a regression model. Then we're going to make sure that it's okay by looking at the residuals. We're going to try our best to interpret the model coefficients and all the other stuff that comes along with it, as well as getting some confidence intervals for those coefficients to see how they behave. And then we want to use the model that we just made to predict or to estimate some unobserved value that we don't have. Okay. So go ahead and open up R and grab the data. The data is in the link in the description, but also if you're in my Stat 3050 class, it's in one of the class folders. You should know where to go for that. But before we get into it, this example was brought to you by these absolute hitters. Good Lord. Right now, I'm listening to a shuffle of both of these albums. I can't play them, obviously, on YouTube because they'll get busted for copyright, but that's fine. You can listen to these as well. Wolfpack, probably my favorite artist, and then Brittany Howard, her album Jamie is super good. She's the lead singer for Alabama Shakes, so if she sounds familiar, that'd be why. Cool. All right, let's get into it. Okay, so we're here, we're set. The first thing I want to do is I want to read in the data. And we know that there's a bunch of different ways we could go about doing it. The way I'm going to do it, I'm going to set my working directory. And I've shown you how to do this in class, but we haven't really done it all too much, but it's pretty easy. Let me show you what I mean by that. So I'll come up here to Session, and then Set Working Directory, and then choose Working Directory, or Choose Directory here. And if I select that, it's going to bring up sort of my folders search window here. I know that my data is saved in this folder here called Simple. That's in my regression folder, which is in this class folder, right? So let me get back to there. I've got it called Regression, and then in there, Simple. If I open that up, it's going to come down here and say, okay, cool. We ran that line of code, even though we didn't see it. It does it on its own. What I'm going to do is I'm going to copy and paste it up here, just so I have it, so I don't have to hit that every single time I close out R. And maybe if I want to run this again, I don't have to come back up here and do all that. So if I run that, it's not going to do anything now because it's already set, but it will set it every time we restart R. Okay, so in my folder, I've got a data set called math_score.csv. So I want to save that as something. So I'm going to save it as, I'm just going to save it as math for now. And then I'm going to hit it with this read.csv. And then, since I've already set my working directory, I can just call in the file name, which is math_score.csv. Now, we could also, just as easily, and let me show you, we could use this file.choose, and I'm not going to save it as anything just because I want to give you the example. But it brings up, when we run that, it brings up the folders window here, and then that's that, right? So, you might have seen like a little hint of it, but this math data set, this math score data set is really interesting. Okay, so this is real. This actually happened. Way back in the day, like in the late 60s or early 70s, there's a study that happened, a legitimate study, where they gave 7 individuals varying amounts of LSD. Okay. And then after some time, they gave them a math test, and they wanted to see, how well they could do on this math test, given that they have a varying amount of this drug in their system. So pretty cool. We can already kind of see that as the concentration here in the first column goes up, this math score goes down. So this math score is like a normal test, right? 0 to 100, 0 being the worst and 100 being the best. And then this concentration here. Not totally sure what the unit is here, but for this example, it doesn't really so much matter. Okay, so we've got that. And what's the first thing I want to do? Let me be kind of organized here. Okay. So I've got that all organized. Well, if we notice, this first column here has this kind of strange symbol. That's going to make things a little difficult to work with. But that's okay, because we have ways we can get around that. So what I'm going to do, I'm just going to rename these column names. How do I do that? Well, I'm going to use this names, and then I'm going to put the data in there, and I've called the data math. And then it's going to get the names of math. It's just going to get C, so that's concatenate, right? So we can give it a list of things. And then the first one is the concentration, right? So it has to be in order of what we have here. So we'll call the first one CONC, short for concentration, and then the second one score. So easy enough, and if we run that, nothing much has changed other than the column names. So we're set. Okay, and what do we want to do next? Well, let's plot some data. Let's see what we're working with. Let me give a little bit more room here. Cool. Okay, so the first thing I want to do is I want to load in the tidyverse. The tidyverse. So when we do that, it's going to load in all of the other packages associated with this, universe of packages. And in that, there's a package called ggplot. So that's already loaded in, so we're good. And this ggplot is what we're going to be using pretty much in all the examples, and especially in this class, for plotting our data. So there's a lot that goes on in this ggplot, which is a good thing, because that means that we have more that we can edit, more that we can tweak. Okay. So the first thing that we want to do is use this data equals, and the data equals math in this case. That's the only data set that we have right now. And then next is the mapping. Okay. So if we're trying to be very specific here, very detail oriented, it's mapping equals, and then it uses this AES function. This isn't totally necessary, so I'm going to get rid of that. More or less, that's just to be very detail oriented. But within the AES, within the aesthetic function here, it takes two arguments, at least two arguments in this case, one x and one y. So one x variable, this is our predictor, and our predictor in this case is this concentration, right? We want to see how concentration affects your math score. Well, maybe not your math score, but the math scores of these people. Okay, so x is going to be CONC, and that means our y is going to be score. Okay, so if I were to just run this, what happens? Well, we see a blank plot with the mapped out variables, more or less the range of the variables, which is all good, but we don't really see anything else, right? Because we haven't told the computer to do anything else, okay? So what we want to do next is use this geom point, and then we can leave that blank. There's really nothing that needs to go on in there. Great question. We use this geom underscore smooth function to map out the line. Okay, so let's leave this blank for now and see what happens when we run this. Well, we get a pretty funky looking plot, and we also see this sort of comment down here. It's not a warning message, it's not an error message, it's just a comment saying that the geom smooth is using method equals lowest. What does that mean? Well, method equals lowest, what it does is it kind of makes a window, makes a line through some window. I think it's 3 points, and then the next window, another line for 3 points, and then the next 3 points, and then a line, and then it smooths it out. And so that's kind of making this sort of curved line here, which is not too helpful to see, especially in this case. It almost flattens it out because of this confidence interval here is so wide, right? So what we want to do is use method equals, and then quotation marks LM. And LM is just short for linear model. There's more things that you can put in here too if you look at the info for this function. But for now, this is all we want. So if we run that, now we see, a nice straight line that has this sort of negative slope, right? So the relationship between concentration and score is negative, right? So as concentration increases, our score is going to decrease, okay? Which kind of makes sense biologically, I suppose. So what do we want to do next? Well, what I want to do actually, I want to clean up the background. And that's just going to clean up sort of that gray background there. And this makes it a lot easier to look at. Maybe if we want to change the color of this line, we can come into Geom Smooth again and just use this COL, short for color, equals, and then we can call it black. And when we do that, we see that it makes this black line. So really whatever, there's a lot that you can do with the overall sort of look and aesthetic of these plots, which makes ggplot really helpful. A little bit better than Basar, I think. But there's all sorts of stuff you can do. So we'll just leave it like that and then say that's that. Well, so what do we want to do next? Well, we're looking at this data, we're looking at this plot here, and we say, okay, it is negative, right? The slope is negative, but we don't know by how much. We could, print out this plot and then get out our ruler and then figure out, sort of what the rise and run is and figure out a slope or whatever. Thankfully, we don't have to do that. We can just use R to do it for us. So we'll come over here and we'll say, okay, let's make a model. Let's make a model, and let's figure out what's really going on over here. Okay, and how do we do that? Well, great question. The first thing we want to do is store it as something, and we'll just call it model for now. And it's going to get linear model, and then within linear model are at least two things that we need to fill out. Okay, the first one being the formula. Okay, this is our sort of formula that we're trying to construct. Okay, so that formula, very similar to the ANOVA stuff that we were working on earlier in the semester, it's the same deal here, right? So it's going to be our outcome and then as a function of our predictor. Okay, so our outcome is score, and then our predictor is CONC, concentration. And then we need to say where it's coming from. So data equals, and I've called the data math. Okay, so if I were to run this, nothing will happen except for the model is being stored over here in the environment. Okay, so that's good. That's cool. So just like with the ANOVA, we use that summary.AOV. In this case, we just want to use that summary.LM, and we can put in our model in there and run that, and let's see what happens. Okay. Cool. Here we are. So we see up here the call that's more or less telling us what we're doing here, just double checking more or less. And then we move down to the residuals. Okay, so this is a good data set because one, it's small. There's only 7 observations. So the residuals here, instead of doing that 5-number summary, it will just give us the residual value for each observation. Okay, so this first one here is the first observation. So if we come over here to the scatter plot, we see that this residual value here is being represented by this 0.3472, okay? And if we were to zoom in way far, right, way far, the distance between this dot, this observed value, and the fitted value on the line is pretty small, right? They're not that far apart. And we see that here, this 0.3472. Right, it's a positive value because the observed value is above the line. Okay, observed minus fitted. Right, that's sort of the formula for it. And then if we move on to our next observation, we see that it has a negative 4.16 residual value, and that's because this observation, this observed value, is lower than the fitted value. Right, so the distance between it and the line is this value here, negative 4.16, and because the observed is below, it's going to be a negative value. Same thing with number 3 here. This third observation is pretty far away from the line, above the line, right? So we have this sort of larger residual value for that, larger positive residual value. And we sort of see the same story for all of the other values too, all of the other observations. So that's good. We'll come back to that in a little bit when we're actually looking at the residual plot, but for now, that's sort of the nuts and bolts of what's happening. Okay. So then we come down to the coefficients table, and we're looking more or less at just 2 things, okay? We want to see what the estimate is for our intercept, our y-intercept, and then the slope coefficient. So this is our beta naught. Beta naught is the intercept, and then beta 1 is the slope, okay? So we see here that we get an estimate of 89.124 for the intercept, okay? And so what that's telling you is if we come back over here to the scatter plot, what that's telling you is if we were to trace that line all the way up, it would hit the y-axis at 89.124, more or less, okay? And then down here for the slope, negative 9.009, right? That's essentially telling us, every time x increases, y is going to decrease by that much, okay? By negative 9.009. So for every 1 unit increase in x, y decreases by beta 1. Okay, so we sort of saw that in those previous videos. But can we trust these values? Well, if we come over here to the p-value for these estimates, we see that they're both fairly below 0.05, that chosen alpha, right? This intercept is way below 0.05, right? It's nearly 0, or it's pretty small at least. And then we see that if we were to round this 0.002, that's fairly decent, right? That's well below our alpha. Okay, so that just means that we can trust these estimates here. These estimates are going to be more or less, quote unquote, correct. Okay, so then we come back down here, sort of ignore this line here, and then come down to the r squared, and we see that it's decently high, 0.8778 or so. Same thing with the adjusted r squared. It's a little bit lower because we have a pretty small sample size, right? So it's adjusting for that, which is fine, which is good for us. And then this last line, for right now, we won't so much worry about it. Well, let's look at the residuals, right? So that's sort of the whole idea, is that we make our model, we give it a quick look over to make sure everything's okay, and then we look at the residuals, right? So the residuals tell us actually if our model is, decent, okay? Not so much the p-values initially. We look at the residuals first and then sort of start making our interpretation of the model, okay? So how do we do that? Well, we'll load in the ggfortify library. And within that library is a function called Autoplot. And within that, we just put in our object equals, and that's just going to be our model, our linear model, and that's going to plot the residuals for us. And if I just run this by itself, it's going to pop up over here on the right. Let me zoom it in here too. We see that, well, this blue line is kind of mucking things up a little bit, right? We do have a fairly small sample size, so we do have to sort of take this by the grain of salt. But let's get rid of this blue line because it's a little bit distracting. So how do we do that? Well, we'll come in here and use this smooth .color with a U. I'm just going to hit tab so I don't have to spell it out. And that's going to be NA. We're going to replace that function there, that argument, with a bunch of NA values, okay? So it's not going to actually do anything as far as plotting. And then let's get rid of that gray background too, just cause. When we run that, we'll zoom it in. And what do we see? Well, what are we looking for? Well, in regression, we have 3 sort of assumptions or 3 requirements to sort of validate our model, at least initially, okay? So the first one is goodness of fit, right? We want to make sure that the data that we have fits around a straight line fairly decently, okay? And so we do have, a fairly small sample size here, so we do have to take it by the grain of salt, which is fine in this case. But we don't see any major evidence of curvature here, right? So our scatter plot was good, right? Our scatter plot, the dots, the points fit around the line fairly decently. And we see the sort of the same thing here with the residuals versus fit. And in this case, the residuals versus fit and the scatter plot of the actual data are going to be nearly identical, okay? Nearly identical. But the same thing, right? We're still looking for that curvature. And if it's there, then we have an issue. We're looking for more or less data that fits around a straight line. Okay, so that's the first one. The second one, and the order matters, right? The second one is this idea of equal scatter, or this homoscedasticity. And what that is we just want to make sure that there's no pattern in the data. There's no clumping on one side of the residual versus fit over here, which in this case we don't really see that. Everything is decently spread out. These two are a little close together, but maybe if we had more data, it would look pretty equally scattered for the most part. Okay, and then the next one, the third requirement, the third assumption is a normal distribution of the residuals. We have two tools that we can use to determine if it's normally distributed. The first one is this normal QQ plot, and the idea here is that each one of these dots here, each one of these points, should be sort of close to or on the line. Okay, and since we have a fairly small sample size, it's not too helpful in this case. And in fact, the histogram, we can do that real quick. The histogram is going to look kind of clunky too, because we only have 7 observations, and it's going to make 4 bins for that. So for right now, this is just an example of an intro into linear regression. For right now, we'll say that this is fine, okay? The histogram is not great. The sample size is fairly small, so that's why we're sort of getting inconclusive residuals, right? So for right now, we'll say that's fine, and then we'll move on. Okay, so what do we want to move on to? Why don't we look at the confidence intervals? I can spell. And how do we do that? Well, we use, real quick, this CONFINT, confint function, and we just put in our object is going to be our model, because we want to look at the coefficients, right? We want to look at the confidence interval for our various coefficients, the intercept and slope in this case. Okay, so if I do that and I run that, we come down here and we get a 95% confidence interval for the intercept and for the slope coefficients, okay? And so what is this telling us? Well, this is saying that if we were to do this all over again and sample the whole population, there's a 95% chance that the actual intercept would be somewhere between these two values, right? And then the same thing with the slope. The slope may actually be between -12 and -5 and some change, right? So that gives us kind of an idea of maybe how the population is behaving. Here's the issue, though, is that we have such a small sample size that we don't really have that good of an idea of what the population is doing, because our sample is fairly small, right? So you'll notice here that these values are fairly large, right? Are fairly large. And they don't really make too much sense on the upper end, at least for the intercept, because we're working with test scores, right? We are working with test scores. And what this is saying is 107.24 or whatever is the value that you would get when x is 0. And don't forget that we are looking at concentrations of an illicit drug, right? And so right now, hopefully, none of you have LSD in your system right now. And if you were to take a math test, you probably would score a 100, right? But you would not be able to score 107.24 or whatever, because that's just not feasible, right? The cap is 100. So we don't really know how the data is behaving. So let me actually give you a better example when we're looking at sort of predicting some new value, okay? And let me actually pull up the scatter plot too. So I've got that over here. Looks good. Looks nice. So what do? Well, we have our model coefficients. So this is my model that I've made, and then I use this $sign to look into the model, and I'm going to get the coefficients. So if I just get rid of that, hit tab here, it gives me all of the options that are within that model object. I just want the coefficients for right now, and if I run that, I'm going to get the actual coefficients, right? Okay, so that's our intercept and that's our slope. So our regression equation, looks something like this. Score is equal to 89.124, we'll say. Let's see, and then minus 9.009. Let me actually round that up just to make it cleaner. We'll say that is, so 89.12 minus 9.01 x. Okay, so that's our regression equation. Or instead of x, we can actually just use CONC here. Okay, so that's our concentration, right? So we say that for every 1 unit increase in x in concentration, y, our math score, will decrease by 9.01 points, we'll say. Okay, so if we come over here to our scatter plot, we'll notice that there's quite a bit of data missing as far as the space in between our first observation and like the next two. So maybe let's do it algebraically first. So we'll copy and paste our equation here. Okay, and then instead of CONC, let's take a look. There's no data here for a concentration of 2. And there's also no data, for anything past this 1.7 or whatever it is, 1.1. So it could be any decimal too. It doesn't have to be this one integer. But just for now, let's predict. Let's see what happens. Let's see what happens when we put in a value of 2. And I have to use this asterisk here because R doesn't look at parentheses as multipliers, which is fine. So if we run that, using R as a calculator pretty much right now, we get a score, an estimated score, of 71.1. And this is very important that we say estimated, okay, because that is what we're doing. So we get the score of 71.1, and this is based on our regression equation. And that's fine, right? That kind of makes sense, at least, given the trend of these data. What about if we were to look at a concentration of 0, right? So no LSD in your system, okay? So all I do is I just put a 0 in there, and I run that, and I don't even need to run it, right? But I will anyway, and we'll see that this whole term here is just going to go to 0, right? 0 times anything is 0, and then we're left just with the intercept, right? Okay, we're just left with the intercept. But does this make sense? Well, maybe, but I think that the math test for this data, for this study, was pretty simple, right? So it's pretty easy to get a 100, okay? And so with nothing in your system, it should be pretty feasible that you get a 100. But our estimated value when you have nothing in your system is 89.12, which is, not, that's fine, a B or whatever, but there's a good chance that you could do better, right? So that's why, and let's come back over here to our scatter plot, that's why we're not really able to extrapolate. We're not really able to, estimate anything outside of the range of data that we have, right? It's kind of against the rules. And in this case, it doesn't really make sense either. Sometimes it may, but a lot of the times it really doesn't, right? So that's why we say, okay, we're just going to predict, we're just going to estimate whatever is in the range of our data and not really too much outside of that. Sometimes you can get away with being a little bit outside, a little bit, but really sort of breaking some rules there. Let's look at the other end too. So I'm going to take this regression equation, copy and paste it again. And instead of 0, let's look at, let's say 9. Concentration of 9. Okay, who knows what kind of time you're having there, but probably not a great time. Okay, so we see that this estimated value is 8.03. Okay, so pretty low, right? Maybe let's go one more. Let's go one more. And let's change this to a 10. All right, here we go. There's some examples here, but in this case, is it possible to get a negative value for a test? Well, no, of course not, right? The cap is 0. The floor is 0, and the cap is 100, right? But our model is saying that if you had a concentration of 10, which, good lord, then your score is going to be negative, right? A -1, essentially. That doesn't make sense, right? In real life, right, biologically, it just does not make sense. So, again, just another example as to why we cannot extrapolate beyond the range of data that we have. I can't estimate outside of that. All right, so. What do we want to do next? Well, using this regression equation here and using R as like a fancy calculator is fine, right? But we can have a little bit more fun with it, I think. So let's take all of these values again. And let's store them in this thing called new underscore data, okay? And all I'm going to do is I'm going to make a data frame here, data.frame, okay? And then the first column that I'm going to call it conc there. And it's going to get, a few values. It's going to get these values that I just did. Okay. And if I run this just by itself and then click on it over here, we see that we get this sort of new column of made up data, right? 2, 0, 9, and 10, right? The data that we were working with earlier up here. And it turns out that instead of using R as a fancy calculator, like we did up here, we can use this function called predict.lm, okay? And within that, there are 2 arguments that we need to fill, and there's a bunch of extra stuff too, but we won't worry about it so much for right now, So if we do object, right, that's the first argument there, and if we just hit tab, it'll bring up all of the stuff, right, all the stuff. The first one, object, we're going to throw in our model that we just made, okay, and then the second object is this new data, okay, and so I've made new data up here, and just a quick note, it does get a little finicky in that your new data, when you're predicting it down here, it has to match the same column name as your data that you've made the model from, okay. But we've already got that taken care of over here on line 78. So if I just put in new underscore data, it's that data frame, what's going to happen? Well, here's what's going to happen. And let me sort of pull, let's see if I can do this. There we go. Cool. All right. So our first value, right, our first one was, let's see, a score of 2, right? And we get this estimated value of 71.1049, blah, 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 all the way out with more decimal points than we got up here, right? Same thing with the second one, third, and fourth, right? We get the same values, except we get a little bit more precision with that, right? It goes off further. But we see that it's doing the same thing, right? Okay, and so that's all good, right? That's all fine. We're using R as a fancy calculator. We're using this predict.lm to get us the same stuff, right? But what if I wanted to make a confidence interval for these estimates? Okay, interesting. We could go in to our intro stat textbooks and look up the formula for a confidence interval and just not have a good time, right? What we can do instead is in this predict.lm function, we can just come down here and our next argument will say interval, and in quotation marks, we can put in confidence. And when we run that, what do we get? Ooh, nice. So we get this fitted value, right? This is more or less the estimated value, right? Same values that we saw before, 71, 89, 8, and -1-ish. And then we see our confidence interval for that value. Super cool, right? So given that you get a concentration of 2, your estimated value for your score would be 71, and there's a 95% chance that it would actually be somewhere between 59 and 82, right? We can be 95% certain that the actual population would be estimated somewhere between these two values, given that score of 2. Sorry, I just hit my knee on my desk and it kind of hurt. Okay, and then same thing with 89, right? Given that the score is 0, right? Given that the score is 0, we see here that we get a confidence interval of 71 to 107.24. Hey, was that not the same confidence interval that we saw up here on line 59 in this confidence interval section? It is, right? It is. It's doing the same thing. It's pretty tight. It's pretty cool. And then we see over here that you have an estimated value of 8, and then, but 95% chance, wait a second, a negative value for a test score, probably not realistic, right? Definitely not realistic. So that's again why we sort of start losing our validity outside of the data that we have, right? In this case, the math doesn't really make sense. We don't know how the data behaves outside of this range, but we do know how it behaves inside of the range, right? Or at least more or less, right? More or less. So that's pretty much the story with predicting values. We can get a confidence interval. We can even get a prediction interval too, and that's going to be slightly different. We won't worry about that in this class. But that's really the main story here, right? We can use R as a fancy calculator. We can use R as a fancy calculator and actually get a confidence interval for these new estimated values, which is really cool. I get super stoked about this. Okay, so that is it for now. Really don't have all too much to say other than, don't do drugs and take a math test at the same time. Don't do drugs and do my project for this class at the same time. I don't think you would have very much a fun time. So that's my advice for you today, and probably it for the rest of the day too, for the rest of the semester. But go back through and sort of review all the stuff that we did here. Maybe go and look at confidence intervals again, prediction stuff if you're interested. The stuff that we're doing here, where we're predicting and getting a confidence interval, we're not too worried about it from here on out, but it is good information to know when your purpose is prediction. Okay, so that's it for now, and I will see you next time.